All righty. Hopefully you can hear me out there. All right, everybody. Well, this is Mr. Rich, so we're going to get going. Let me see. Can somebody confirm that you can hear me? Yes, Rishi says he can hear me. That's a really weird avatar, Rishi. That doesn't look like you. But then again, my avatar doesn't look too much like me because that was like 10 years ago and about, I don't know, 70 pounds ago, maybe. I don't know. All right, well, welcome. We're going to do a quick review for Calc AB because the test is just about 11 hours away. And so I've got some problems that I'll go over. And I don't know, I guess if you have some questions, you can pop them up there and I can address them. Okay. All right. So most of you are from my class. There's a few of you that have joined that aren't really in one of my classes. Wow, Jacob. Way to go, Jacob. I'm seeing Jacob. He's one of my stat students. I like your avatar there, Jacob. Pretty cool. And Jordan was asking me what music that was. It's called Night Driving. I don't know what that is, but it's called Night Driving. Shawnee, oh my goodness. My hat says, I guess you guys already answered it. Math. It's a political hat, actually. One of the political candidates in 2020, I guess it was, this was his hat. So, but I didn't buy it for that. I just bought it because it says math on it. All righty. Why am I so cool? I don't know. Nobody really usually thinks I'm very cool, but I appreciate that, Shawnee. Well, let's get into a few tips. Yes, Elliot, that is true. Andrew Yang was the guy who was the. I forget why he was big on math, but anyway, I don't know. That was his hat during one of his hats during the political campaign. I do get comments on this hat when I wear it out in public. Usually they're positive. So, all right, who's just having fun? I mean, you know, that's Stanley. Okay, what's up, Stanley? Who's just having fun? I don't know. Cool. All right, so what I'm going to try to do here is share my screen, and let's see if we could make that work. Let's try it here. Let's see. Yeah, there we go. So I think you guys can see my screen right there. And we're going to work through a few problems. And feel free to ask questions or say that you want to look at some other kind of problem, and I'd be happy to do that. I don't know how long I'm going to go here. If you get tired and have to go to bed, just drop off. That's fine. But let's just do it. So my first tip that I was going to tell you about is to know your table of derivatives and integrals, right? You don't want to lose any points because you didn't remember one of the rules on your derivatives table. And I'll show you a few examples of that right here that might maybe be a rule that you might tend to forget, or that students typically will forget on the multiple choice portion and might miss a point or two. So let's look at this first antiderivative here. So this antiderivative, let's just talk about what it's not, right? I've been emphasizing this in my class that this is not equal to the natural log of x squared plus 4x plus 5, right? That is not what this thing is equal to. if I have a linear function down here, then yeah, I could use u substitution, and then this would turn into a natural log. You can't use u substitution on this. That's not going to work. You could try it, but it's not. So one of the things that this requires you to recognize is that this is going to be an arctangent antiderivative. Now, this might be one that you'd be more prone to see on the BC exam, but this one, I believe, can pop up on the AB exam as well. So what I'm going to do is I'm going to complete the square so I can get this into an arctangent antiderivative. The rule that I'm talking about is the antiderivative of 1 over x squared plus 1 dx. That is the rule, which would be the arctangent of x plus c. And so what we can do here is we're going to actually complete the square on this x squared plus 4x part, and we'll move that 5 over. And completing the square means I'm going to take half of my 4, which is 2, and I'm going to square it. So I'm going to put a plus 4 right there. But then that means that I need to balance that with a minus 4 over here. And the whole reason that I completed that square was so that I could then rewrite that integral as 1 over then x plus 2 squared, combining those two together, plus 1 dx. And then I can see that this fits the pattern of this rule here, and I can call this arctangent, right? Tangent inverse or arctangent of x plus 2 plus c. All right, so that's one rule here. Let's talk about this rule here on derivatives. If I'm going to take the derivative of some arbitrary base log base 6 of 7x squared. Well, the rule here that we would be talking about would be d dx of log, we'll call it base b of x. Well, this is going to be 1 over x, and then I would have to multiply that, though, by the natural log of base, natural log of b, like that. Noah is asking us a question here. How do you, oh, nice avatar. Wow, eating an ice cream cone. Wow, pretty good, Noah. How do you know whether to use arctan or partial fraction decomposition? Well, actually, I think you could use either one there. Because, right, this one, I could factor that. Could I? No, I really can't factor it. I have to, if I'm going to use partial fraction decomposition, I want to be able to factor this. And that's not factorable, so I can't really split it up into 2. So that's what I would say to that. But now, if I'm going to take the derivative here of, and partial fraction decomposition for the Calc AB people is something that we cover in more of the integration techniques in Calc BC. So you'll see that next year if you happen to go that route. Anyways, so what I'm going to do here is I'm going to use the chain rule along with this rule right here. So this is going to be 1 over the argument 7x squared. And then I have to multiply that, though, by the derivative of the 7x squared, which would be 14x. And then I would then have to multiply that by the natural log of 6. So if this was a multiple choice problem, it would probably be simplified, right? I would combine this to be 14x natural log of 6 over 7x squared, which would then, looks like it would be 2 over x times the natural log of 6, or maybe the natural log of 6 would be up in the numerator. But that's a property of derivatives, or I should say a rule of derivatives that you want to remember. All right. Wow, we got 38 people. I was talking to one of my students today that I tutor, and I was saying I'll probably get, I don't know, maybe 5 or 6. I was trying to think, usually maybe 10% of my students will show up, but that's pretty good turnout. I appreciate it. Very good. And usually it's not the people who are trying to go from like a 1 to a 2 or a 2 to a 3 who come to get help. It's usually the students are trying to get 4s or 5s. So maybe that says something about all of you. Awesome. Okay. I don't recognize some of these people. Bilardiodisha. Sorry, typo. Okay. I appreciate you. No, Stanley, I appreciate you. Okay. I really appreciate you, Stanley. Stanley's a BC student. Okay. William Lee. No way, Mr. Rich. Next, I think Noah's saying, please move along, Mr. Rich. Please move along. All right, let's do some other problems here that I think might be helpful. What was I doing here? Let's see. Well, let's talk about total distance traveled. How about that? So a particle moves along the x-axis. The velocity of the particle at time t is 6t minus t squared. What is the total distance traveled by the particle from time t equals 0 to t equals 3? Well, if I'm calculating total distance traveled and I know the velocity function, right, my total distance traveled is going to be my integral over my interval 0 to 3 of the absolute value of the velocity function. Absolute value v of t dt. Now, in a problem like this, I want to sketch what I think this function would look like, right? So I've got my velocity function, and I can write that in factored form, like that. And that tells me that I've got intercepts at 0 and 6. So this is going to be a parabola that, as you can see, is going to do something like this. And so if I'm going to integrate it from 0 to 3, then, gee, that's good. I know that this thing is always going to be above the x-axis over my interval. Wow, I'm getting comments here. I'm getting actual text messages too. I got you, Noah. Yep. All right. Anyways, so I'm going to go ahead and integrate this. And I can drop my absolute value signs here because I know that this is going to be a positive section of my function from 0 to 3. So I'm going to take the integral from 0 to 3 of 6t minus t squared dt. Take the antiderivative of that. So I'm going to take this in 2 parts here because I got 2 terms. So that's going to be 3t squared. What's this going to be? My goodness. So if I take the antiderivative of t squared, that's going to be t cubed over 3. And then I'm going to evaluate that antiderivative from 0 to 3. So that's going to give me 3 times 9 minus 27 over 3. Okay, minus 0. I'm going to evaluate that at 0. So it looks like I've got 27 minus 9. It's going to give me 18. I'm going with letter D. Going with letter D. All right. How's that look, Rishi? Yeah, that's right. I forgot. Jacob, I guess you're a Calc AB. You're just not in my class. Jacob Dietrich. All right. So anyway, so that's total distance traveled. All right. So let's go back to another tip here. So my second tip is review the theorems and the conditions for them. That's probably not proper English, but you need to know your intermediate value theorem, your mean value theorem, extreme value theorem. What other theorems? But know the conditions under which they apply, right? In terms of continuity and differentiability, because when you invoke one of the theorems as an answer in a free response question, you do need to lay down the predicate as to why you're using those theorems. L'Hopital's rule, for example, and I think I have a problem here on L'Hopital's rule that we'll cover. Okay, so that was my tip number 2: is review your theorems. All right. Yeah, yep, Shalini, yep, there's lots of fundamental theorems. They're very fundamental. So that's one thing to remember. Those fundamental theorems, extremely fundamental. Yeah, I've been waiting for fundamental theorem part 3. I'm not sure when that's coming out, but parts 1 and 2 are pretty good. Part 2, I think, was a little better made than part 1, but anyways. Okay, let's see. TRR, I do not know who TRR is, but it says, because we know the graph of V of t function is positive over the given interval, we don't need to take the absolute value. Right, because when we take the absolute value of our function, let me go back to the screen here. Make sure the calculator doesn't give out on me. Let's go to this, and we shall remove your question there, TRR. But yeah, the absolute value just means that any part where my function would have dipped below the x-axis, I would have had to integrate that separately and then take its absolute value. For example, if your function is looking something like this, and you're integrating from here over to here, right? What you have to do, if this is my limits of integration, I would have to break up my integral and integrate to find this area right here. And then I would have to set up a separate integral and integrate over that interval right there. And then this would be obviously a negative answer. And then I would turn that positive and then add it, right? If we're talking about total distance traveled and we're talking about integrating velocity, this right here is movement to the right over this interval. Okay, and then the object is stopping and then it's moving left over this interval. So if all I do is take the integral of my velocity, I'm going to end up with displacement. Okay, and that'll give me the ending position. It'll give me the total net change in their position over that time interval. But if I'm doing total distance traveled, I don't want that. I want to include all of these distances as positive values. Okay. All right. Next, let's see what other beauties we've got here. Let's try, I want to try this one here about continuity, because it's very likely you'll see a problem that is going to involve continuity. And I told my students this this coming week. I told them that if you're dealing with a free response question on continuity and you're not using limits to express your answer, then you're not going to get full credit, okay? Because continuity comes from taking the limit as you approach the point where you're determining the continuity. This question here that I'm showing you is an interesting question. This is another, this question, I think this is a Brian Passwater question. Brian Passwater is one of the teachers that does he's an AP teacher from Indiana, and he does some of the videos, and he did the BC videos for us this year. I think he did a lot of the daily videos, and he did the review videos with his buddy Tony up there in Indianapolis. And this was a preparation problem he did when we had the COVID problem back in 2020, and he came up with these set of problems for us to study from, and they ended up being very close to what the actual test looked like. But they're really good problem. So this one, it looks pretty busy here, but it's showing a graph of f prime, okay? And then they give us a function g of x, which actually includes f of x squared minus 5 within the function. So they are connected in that fashion. And this says that the function f is twice differentiable on the closed interval, -2 to 10. It satisfies f of 6 equals -4. The graph of f prime, the derivative of f, is shown in the figure above. The graph of f prime has horizontal tangent lines at 2, 5, 8, and 9. Okay, that could be determined here by looking at it, but he's telling us basically where these relative max and mins are. The areas of the regions between the graph of f prime and the x-axis are labeled in the figure. So the first question that he started off with on this set of problems is show that G is continuous at x equals 3. So I'm going to lay down what the predicate is, right, for showing that a function is continuous at a particular value of 3. For G to be continuous at 3, right, the limit as x approaches 3 from the right has got to be equal to the limit as x approaches 3 from the left. And so I'm going to see if that is true. I'm assuming it is true because it's wanting me to show that it's continuous. And so I'm going to do that. Now, through how do we evaluate limits? We always start by evaluating limits through substitution. So I would say here on the left-hand side that this would be f of 3 squared minus 5. Okay, because that's my g of x. And actually, that's to the right. So I'll put that, that's actually to the left. So this is f of 3 squared minus 5. And then as I come in from the right, it would be on this piece right here, which would be 5 minus 2 times 3. This 5 minus 2 times 3 is going to be a -1. And this would be f of 4, like that. Now, how do I find f of 4? That becomes the question. Now, this up here is this function that I'm looking at here is f prime, right? It's not f of 4. So could anybody comment as to how it is that we could determine what f of 4 is? And I'll look over at the comments here and see. Anybody? How can we find f of 4? What's up, Joseph? Yeah, so William says maybe integrals. Yeah. So I want to take an integral. Now, what I'm going to do is I'm going to take an integral from a position that I know and then integrate to the position where I'm trying to find my value of my function. And that is because that an integral is basically accumulating the change of the function over that time. Okay, so over that interval. So what I could do is I could say that my f of 4, okay, is going to be equal to f of 6 plus the integral from 6 to 4 of the f prime of x, right? That's where I want to integrate my f prime of x to get f of x. And so what would that be? Well, f of 6, and now remember, what am I doing here? I'm saying that this y value right here, which I know is -4, right? That's my y value where x was 6. So therefore, I need to start my integral at 6 and then integrate to the value that I'm trying to find my function f at. So I am going to then evaluate this and say, well, f of 6 is a -4. And when I come up here and look at what would be the integral from 6 to 4, right, integrating back this way, 6 to 4, well, this area is 3, But if I'm integrating backwards, it would be it would end up being a positive 3. Stated another way, some of you might like to see it better this way. I'm going to change the sign on that integral to make it 4 to 6 f prime of x dx, like that. So I can flip those integrals. Now it's a minus. So this is -4 minus. Now what's my integral from 4 to 6? It's a -3, because that area is underneath the x-axis. And so this is a -3. And so this ends up being -1. So indeed, -1 is equal to -1. And I have shown that my function is continuous. Now, so what I can say is, here is, because my limit as x approaches 3, and I'm going to say it this way, as my limit as x approaches 3 of my g of x, this is g of x, is equal to -1, which is to say that the limit exists and it's equal to 1, and g of 3 is equal to -1, then g of x is continuous at x equals 3. Right? Those were the conditions for continuity at x equals 3. Is the limit has to exist at the point where we're evaluating the continuity, and which means the left and right hand limits have to be the same, and it also has to be the same as the function evaluated directly at that point. All right, it is 9:45. We'll keep going here. Lamborghini Aventador says, try not to get the early grind in. Okay, not sure what that means, but I'll say I agree with you. Next. Let's try another one. Let's go down here and see what we got. All right, so let's try U substitution. Now, this was another one of my tips. I don't even know if I put it up here as a tip. Well, I'll say it as kind of a third tip. Know the uses of different, oh boy, that doesn't make any sense. So know the different uses of integration, right? And so we know when we first started learning about integration that when we take a definite integral, we are finding area underneath the curve, underneath the function, and trapped by the x-axis, right? So that was what it was. But we also know various uses are, just like I just showed you there, was that integration gives you the accumulated amount of change when you take the derivative of, when you take an integral of the function's derivative, right? I'm able to accumulate the net change over that interval. And we also, there was another use of integration where we were finding an average value, but average value is just finding the area underneath the curve and then dividing by the width of the interval. Now, I want to talk a little bit about integration here in terms of U substitution. So you'll see multiple choice questions like this where they want you to set up an equivalent integral using U substitution. And in this case, they've actually given you the substitution to make here. So one of the things that we have to do when we do U substitution is we are going to have to convert the limits of integration, which are in this case x values, because this is being an integral with respect to x. So right away, I might be able to get rid of some answers here. Because I'm going to plug this 1 in here for x, and u becomes 1. So when x is 1, u is 1. And when x is 4, u should be 2. Right? Square root of 4. So I'm thinking, right? I am thinking that I'm probably going with C or D, but let's see what happens here. So I would set up my integral and say, well, this is going to be e to the u. like this. And then I've got over the square root of x over u. Not sure. Let's try this and see what happens. When we do u substitution and we define u to be the square root of x, we then say that du is the derivative of that, which would be 1/2 x to the minus 1/2 dx, which, as you all know, is 1 over 2 square root of x dx. That's my definition of du. And I go about doing my substitution here. I do have e to the u. That takes care of that portion of my integral. And then what I need is dx over the square root of x. That's the other part that I need to make a substitution for. And I can create that by multiplying this definition of du by 2 on both sides. So this becomes 2 du is equal to 1 over the square root of x dx. So I put a 2 here, and I put a du out here. And I do change my limits of integration from 1 to 2. And it looks like I'm going with C right here. That is that. Just a simple U substitution. Dave Patel. What in the world? How you doing, Dave? My goodness. All right. Dave Patel is live and in person here. That's pretty cool. All right. Anyways, don't cause any trouble, Dave. Noah said impressive. Yeah. What's impressive is your avatar eating the ice cream. Now, let's see what else we've got here. I want to do another problem from this set of problems. And I think in most of my calc classes, we worked a good number of these problems from the AP Calc A to Z set. The BC students, I don't think you saw any of this, but there was one problem that I wanted to go over, maybe not spend a lot of time on it, but it had to do with L'Hopital's rule. And it's pretty fairly likely that you'll see a L'Hopital's rule problem, certainly in the multiple choice. That's a given. But you could also see one on the free response part of the test. And here's one that combines multiple parts on a L'Hopital's rule. So multiple parts on a limit that involves L'Hopital's, but also involves integration, right? So from both first and second semester. But whenever we try to evaluate a limit, we do it through substitution. And so the first thing that we would do is we would try to evaluate this by doing substitution for x being 2. And this would look like this when I try substitution. And this would be sine of 0. I'll just write that in there. And then what you would have to do is figure out, well, gee, what is the integral from 4 to 2 of f prime of t dt? Well, in this particular problem, they did give us a graph of f prime of x. And here's a point that I want to make. You could evaluate. There's nothing that says, hey, that you couldn't evaluate this by taking the antiderivative of f prime, which is f, and then evaluate it using the fundamental theorem of calculus, which would make this f of 2 minus f of 4. Okay, because that's what this would end up being when I evaluate it with the fundamental theorem. But that doesn't help me in this particular problem because I really don't know what f of 2 and f of 4 are. My graph is f prime of x. And so I have to come up with an alternative method, and that is the method of knowing that what does an integral of a function represent? A definite integral with limits from 4 to 2. It means the area under the curve. So I could use geometry here to figure out what this area is bounded by this function between 2 and 4. that area is 2. 1/2 base times height is 2. It would be a negative 2, though, because I'm integrating backwards from 4 to 2. So this actually is 0 over 0. I've also trained let's see, what's Joel? I'm definitely going to listen to Joel here. I'm pretty sure you can just use the what question for this question instead of L'Hopital's rule. I'm not sure what you're talking about there, but anyways, I've told everybody, do not write this on your test. Okay, that's like being not nice to the grader. They're going to take points off usually if you write 0. If you say something is 0 over 0, right? Nothing is 0 over 0. 0, 0 doesn't mean anything. Doesn't it, so you don't write that. If this is a free response question, be sure that if you're going to invoke L'Hopital's rule, which is what you have to do at this point, that you take your time and you say that the limit as x goes to 2 of the numerator, and I'm not going to write this all out, but I would write my numerator and I would say that's equal to 0. And then I would say the limit as x goes to 2 of my denominator, that's equal to 0, right? So I show that. And then I would say, therefore, by L'Hopital's rule, and don't abbreviate it, right? Go ahead and, even if it's sloppy, write it out. Okay, by L'Hopital's rule, then write out an equality. Write out the limit as x goes to 2 of, write the original one, I'm not going to write it all out here for time's sake, is equal to, and then you take the derivative of the top and bottom. That's what L'Hopital's rule says when you get an indeterminate form of 0 over 0, like we did in this case. And you take the derivative of the integral of 4 to x. Well, how do we take derivatives of integrals? Well, as long as I have a constant on the bottom and a function of x on the top, I can take that function of x and substitute it in all occurrences of the dummy variable. That's going to be, and the derivative will cancel out the integral. So this becomes f prime of x plus 1. Because the derivative of x is 1. By the chain rule, I can take the derivative of sine of x squared minus 4 and call it cosine of x squared minus 4 times 2x by the chain rule. And now I can evaluate that. I'm not going to go through it, but that ends up being 3/4, because I can look up f prime of 2 from the table up here and plug that in. I will say this, don't take that shortcut. Right? When you're actually doing this on the test, show your work, right? Show your steps. Go ahead and show that this is f prime of 2 plus 1 cosine of 0 times 4. Okay, and then that's going to get you to 3/4. Okay, William has a good question. Oh, he's invoking Mr. Peterson. What if we wrote that limit 0, 0 instead of equals 0 over 0? No, don't do that. Don't do that. I mean, do that if you want to risk losing points. I mean, I'm seriously. So you don't want to do that, because it's not approaching. I guess what you're saying is that approaching 0, 0. No, it's like saying I'm approaching abidi babidi babit. I mean, what does that mean? It's nothing. It doesn't mean anything. Now, I think I told some of my students too that we've been preaching that, don't write 0, 0 forever. And it just turns out last year that the head grader on the L'Hopital's rule problem said that if you did this, if students did that they took that and as justification for L'Hopital's rule. But don't do that, because I don't think they're going to do that ever again. I just, the norm has been that you have to show that the limit of the numerator and denominator separately are going to 0, if that's what they're going to, and then invoke L'Hopital's rule. All right. Do better next time, Will. Yeah. Yeah, I don't think so, Will. I wouldn't try that. Let's see what else we've got here. Another rule, another. All right, so another tip here. Prep your calculator, right? Be sure to charge it if you've got one of the fancy colored TI-84s. Or change your batteries or take at least a spare set of batteries if you've got the old TI-84, and make sure your calculator is in radians mode, right? Don't make that mistake of doing calculator problems with degrees. That definitely won't work out too well for you. I guarantee you that. Okay, let's do some other ones. All right, let me just open it up though to see if anybody has like a particular type of question that you'd like to see. Oh, Shalini, about the second derivative test. Yeah, sure. So let's see if we could do a second derivative test. Yeah, second derivative. I assume you're talking about maybe the second derivative test for relative extrema, maybe. That's usually what we're talking about there. Let's add a page here. Rishi said related rates. All right, we can do related rates. Yeah, so we always have to use radians when we're doing graphing trig functions. Doing any trig calculations with functions, we got to have it in radians mode. All right, I'll mention something about the second derivative test for relative extrema. That usually is going to come into play when you've got a polynomial. Let me maximize my screen here. Let's go full screen and get rid of the wonderful tip there. But it usually comes into when we're trying to find relative extrema. Let's just do a real simple one here. I'll make this up. Right, so if I'm trying to find relative extrema and I do the first derivative test, I'm going to find my critical values by setting my first derivative equal to 0. And this obviously is x equals 2. Now, what we normally do, and I realize this is a parabola, this is super simple, but if this was a more complicated polynomial and maybe I had two critical values, what I would do, or even if it's not a polynomial, once I've determined what my critical values are, I'm going to take an x value on either side and evaluate what is my derivative on either side. Okay, and that's going to tell me the behavior of f of x on either side. And so I would plug in my -3 over here, and that would be a negative value. And when I put in a let's see, -3 and -1. Did I do that right? X equals 2. Oh, this is, what am I doing? That's 2. So this would be a, I could use a 1 and a 3 right here. All right. And then when I plug in x equals 1, I do get a negative. When I plug in 3, I get a positive. Now, why did we do that? Because we're trying to see what's the behavior of f of x. So it's going from negative to positive. And so that tells me then that this is a relative minimum. I knew that. There's a parabola that opens upward. And so I knew that. However, what the second derivative test says is that if you take the second derivative and it's 2, what you can do is you can take your critical value and plug it in to the second derivative, and it'll tell you the concavity at that location. Now, this was a quadratic, so my second derivative is 2, which means that it's always concave up. But if you plug in your critical value into the second derivative and it turns out that it is a negative value, that tells you two things. It tells you that the function is concave down because the second derivative, if I evaluate it to be negative, but that also tells you that it is a relative maximum. Okay, so if you use the second derivative test and you find out that f double prime of my critical value 2 is greater than 0, then we can say that f of x has a relative minimum at x equals 2 because f prime of 2 is 0. Or let's state it this way. We could say because f prime of x changes from changes from negative to positive. Because that's what that would tell me, right? That if it's concave up, and I had already determined that that was a critical value. So it basically eliminates the need to do that. You can go straight from finding your critical values to evaluating your critical values at the second derivative. And if your critical values have a positive second derivative, that means that it is a relative minimum. If it turns out that your second derivative is a negative value, that means it's a relative maximum. Now, what happens though is if your second derivative is equal to 0 at the critical value, then it means that it's indeterminate. You have to then check your number line analysis there. So I don't know, Shalini. Hopefully that helps. And Joel, wait a minute. I got some good comments here. Okay. I'm looking at these comments. What does DN and YM stand for, Joel? I will need you to explain that one to me, please. I'm with you, Antonio. Joel's using some unsubstantiated, undefined abbreviations. He must work for the government. Anyways, all right. I'll let you guys sort that out. Why did okay, Tyler? Because of the Red Sox. I mean, why else? You know, why are the Rays awesome? The Tampa Bay Rays. They're the Rays. I mean, what can you say? No offense, Tyler. Okay. All right. So you all said related rates. Let's do related rates. Man, oh man, where am I going to find a related rates problem? I think what I'm going to do, I'm going to go back here and go retrieve a related rates problem. I'm a Florida Gator fan, if you didn't know. All right, related rates. Let's do an actual related rates problem from, I don't know, the recent past. I think I got it here somewhere. I have a great set of FRQs that, oh yeah, let's do this. We shall bring this over into our live stream. Yeah. Okay, man. Oh man. Let's get this thing back up. Let's see if that adds. There we go. I want to see my wonderful face here though too at the same time. So maybe I'll do that. Yeah, that's awesome. All right, related rates. Man, I don't know which related rates to do. I'm so tired of doing cone problems. But maybe parent-child relations. Okay. Oh wow, Noah's saying error bound. Yeah, that should do. Okay, well Noah, I would do alternating series test, but this is a Calc A/B. I'm not enough qualified to be doing Calc BC stuff here yet, so no alternating series test tonight. How are these rates related? Oh boy, I don't want to go down that road. All right. Well, class, let's do, I think maybe, let me try to find a good one here. Let's do a sphere problem with no picture. How about that? Okay, so here we go. At time t, t greater than or equal to 0, the volume of a sphere is increasing at a rate proportional to the reciprocal of its radius. Oh my goodness. All right. At t equals 0, the radius of the sphere is 1, and at t equals 15, the radius is 2. The volume V of a sphere with a radius r is V equals 4/3 pi r cubed. Wow. Find the radius of the sphere as a function of time. All right. Well, that should be pretty straightforward. The thing about related rates is we're taking formulas that really don't have anything to do with time, and usually in the realm of geometry or trigonometry, and then we introduce time by taking the derivative with respect to time on both sides of the equation. So what should we do here? So we'll take the derivative on both sides with respect to time. So basically the move that we're making is this right here, doing ddt on both sides of this thing. The derivative of v is 1, and so that's going to get us dv dt. So 1 times then dv dt, right? So basically this relates back to implicit differentiation or the chain rule. When I take a derivative of a variable that's not the same variable as what I'm taking the derivative with respect to, which is t, then I have to tack on a dv dt in this case. Next, I would take the derivative on the right-hand side, 4/3 times 3. This gets me 4 pi r squared times then dr dt. All right. And then what are we going to do next here? Okay, so we've got that. But now, what are we going to do here? The mistake that most students made on this test is they just went ahead and solved this for r, and did the algebra here to solve for r. But it really requires us to do something else here. See, when they tell you on a related rates problem that the volume of a sphere is increasing at a rate, so that they're telling me something about dv dt right here at a rate proportional to the reciprocal of the radius. So it's a direct proportionality. So it's a k to the reciprocal of the radius. Well, that would be times 1 over r. And I do not know why I'm writing at a 30-degree angle right now, but that is what dv dt is. So dv dt, according to that, is k over r. So I can then do that substitution right here. So I can say, well, dv dt, they told me, was k over r. And that's important because if I'm going to solve this for r, I need that r to be right there. Right? That's because v is a function of the radius. All right. All right. Now, what am I going to do? What should I do here? Doesn't say what you have to do, right? What we have to do in this case is I have to solve a differential equation. Right? If I'm going to solve for r and I got dr dt, I don't want to have r equals and then on the other side of the equation I got dr dt going on. So what I want to do is I'm going to bring this r over to the right side to be with the r and the dr. I'm going to bring the dt over and make that k dt. And then I'm going to integrate both sides. Like that. So this is going to be KT. Now, ultimately, I'm going to be solving this for R, correct? Yeah, find the radius of the sphere as a function of t. That's, when you look at this class, this is why you can't have any r or dr dt on the other side of the equation. It has to be a function strictly of time. So, but this is going to be kt plus c. I'm going to put my constant over on this side because what I'm going to end up doing is solving this thing for r over here. All right, so what does this become? This looks like it's going to become pi r to the fourth. Okay, is what I have over there. They did give me some initial conditions, I believe. They told me at t equals 0, the radius of the sphere is 1 at t equals 0. So I'm going to plug in here when t equals 0, the radius is 1, they told me. Yeah. And so that would mean then that 0 plus c is equal to pi times 1. So that tells me c is going to be pi. Okay. But I need to know what k is. So, but I'll go ahead and put this in here. kt plus pi is equal to pi r to the fourth. The other initial condition they told me was that at t equals 15, the radius is 2. Right? So the radius was 2, or 2 to the 16th. So now I need to solve this for k. So 15k is equal to 15 pi. This is 16 pi minus pi is 15 pi. Wow. K is also going to be equal to pi. So what do I have now? I've got pi t plus pi is equal to pi times r to the fourth. Well, pi's are going away. I'm dividing everything by pi. I get t plus 1 equals r to the fourth. R is equal to t plus 1 raised to the 1/4 power, or the fourth root of t plus 1. So that is crazy. That's crazy, because this is a problem that is a related rates problem, but then it ends up being a problem that we have to solve by solving a differential equation. All right. Who is just having fun? I mean, who is that person? Anyways, I'm trying to out somebody who's trying to be anonymous. Okay. That was not a very fun one, but at what time t will the volume of the sphere be 27 times its volume at t equals 0? Let's do another one of these. Let's do a more standard one. Maybe let's do one that involves trigonometry. These show up from time to time. I see these more often, I think, on multiple choice problems, but this year they actually did do one on a free response. So let's get rid of that, zoom in a little bit more on this. All right, we've been going an hour, so, and I still have 31 people. Some people have dropped off, but we're still going here. All right, so ship A is traveling due west toward Lighthouse Rock at a speed of 15 kilometers per hour. Ship B, this ship A is traveling in this direction. Ship B is traveling due north away from Lighthouse Rock, so it's going up in this direction at a speed of 10 kilometers per hour. Now, that means that I can, since this is labeled as x, I know what dx dt is. Since ship A is moving towards the lighthouse, that tells me x is decreasing, so therefore that is a negative 15. dy dt, because the ship is moving away and y is increasing, then that has to be a positive 10. And let x be the distance between ship A and the lighthouse, and let y be the distance between ship B and lighthouse rocket. Time t is shown in the figure. All right, so find the distance in kilometers between ship A and ship B when x equals 4 kilometers and y is 3 kilometers. This is known as the easiest point ever earned on an AP Calc free response question. G, when x is 4 and y is 3, I'm going to use Pythagorean theorem. I'm going to call this thing right here, I'm going to call this r. I'm going to say r is equal to the square root of 3 squared plus 4 squared, otherwise known as 5 kilometers. And you might say, gee, that, why did they ask such an easy question? Well, usually when they give you a question up front, it's something that maybe is almost like a hint that something that you might need that later, right? Okay, so that is A. And then B says, find the rate of change in kilometers per hour of the distance between the two ships when x is 4 and y is 3. This requires us then to set up a some sort of a relationship between these quantities. Now, I'm trying to find the rate of change of the distance between the two ships. So what I'm trying to find is dr dt. When I'm calling r, I need to know the rate of change of that distance between the two ships at this precise moment in time. And so I need a relationship between these, and that's really easy, right? It's going to be x squared plus y squared is equal to r squared. So kind of in part A, that is kind of planting in your mind that, hey, Pythagorean theorem might be the way to go. That's the formula that I'm going to use to set up this relationship. But time is not a factor in this geometry equation, but I can make it so by taking the derivative with respect to time on both sides. So 2x times dx dt plus 2y times dy dt and equals 2r dr dt, like that. And we're trying to find dr dt. So I've got everything else that I need. We're talking about when x is 4, so I'm going to plug in 4. I know that dx dt, I already established that's a negative 15 plus 2 times my y value they told me was 3. Dy dt, I had already determined that was a positive 10. Okay, I could have gotten rid of the 2's here. 2 times r, which we had just determined to be 5 at that precise moment in time. R is 5, and then there's your dr dt. And then that's just, let's get rid of these 2's here. Okay, so I've got negative 30, sorry, negative 60 here, plus 30 is equal to 5 times dr dt. Dr dt. So this is a negative 30. Tell me if I'm making a mistake here, class. Negative 30 equals 5 dr dt. And I might be testing you here to see if you can pick up on my mistakes. Okay, Antonio, I don't know what that means, and I don't want to know what that means. Okay, negative 6. Negative 6. All right, so that tells me at that moment in time that the distance between the ships is decreasing at that rate, at 6 kilometers per hour. All right. Man, people are really dropping off now. Okay, now let's look at C. This is the reason why I picked this one, because I wanted to talk about how to find this. It says, let theta be the angle shown in the figure. Find the rate of change of theta. So they want us to find d theta dt, like that. So that means that I have to find another relationship that would relate the thing that I'm looking for here, or its derivative, d theta dt, and the other quantities in this problem. That looks like it would be tangent. So I can say that part C here, that tangent of that angle theta would be equal to y over x. That is what tangent of theta is equal to. And then what we want to do is we want to introduce time into this equation. So I'm going to take the derivative with respect to time on both sides. Now that's going to require me to do the quotient rule. I know that the derivative of tangent is secant squared. And I'm going to have to do low-d high, high-d low, square the bottom, off we go. So low d high minus high d low all over x squared. It's going to look like that. And I know the things that what am I trying to solve for here? Oh, and I forgot here that when I took the derivative of this, that introduces, right, my d theta dt right here by the chain rule. Right, so I have d theta dt times secant squared theta. And I'm solving this for d theta dt. So what I'm going to do here, I'm going to isolate d theta dt by dividing by secant squared theta on both sides. So basically what I'm doing here is I'm taking all of this that I had and I'm going to put in the bottom, I'm going to put secant squared, x squared, and then secant theta squared is what that ends up being, like that. And then I'm going to plug in what I know. We were talking still about the moment in time when x is equal to 4 and y is equal to 3. But now at that moment in time, when y is 3 and x is 4 and this is 5, well, I know what secant is. Okay, so secant theta is the reciprocal of cosine. So it's going to be basically 5 over 4. Right? Secant is going to be 5 over 4. So this ends up being x squared, which we said was, what did we say that was, 4? Yeah. So this is going to be 16. This is going to be 5 over 4 squared. And then my x up here is, oh, this was dy dt right here. Dy dt. And so my x was 4. And you can see where this is going. The dy dt we said was a positive 10. Minus my y value was a 3. Was a 3. And then this was a negative 15. The dx dt was a negative 15. There you go. You could leave it like that, right? Once you get the numbers plugged in, you could leave it like that, or you could then evaluate it all the way from there. Ends up being 17 over 5. Okay. All right, class. Let's see what else I got here for you. Just tip 5, right? Stay cool, get the low-hanging fruits, right? I've told you guys all year long that it takes about half correct on the multiple choice and maybe half on the free response, and you're in the range of a 3. Right? That doesn't mean that you can get by with like knowing half the material, right? It's just that the level of difficulty of this test is such that that's where students end up that know the material fairly well, end up at around 50%. So when you're going through the test on the multiple choice, it's just like any other standardized test. I always tell students to make a have a two-pass system, which is to say, you want to go through your multiple choice questions and do all the ones that are easiest for you, that you kind of immediately know how to get them, and you can get them within about a minute or less. If not, then skip it. So make one pass and get all the easy ones, then go back and pick up the next easiest. And if there's some that you just don't know how to do, or that you, after a minute, you're like, I have no idea what's going on, then don't make anything up. Don't make your own method of solving it. Just trust to luck and guess on that answer. Okay. On the free responses, the best advice I can give is be sure to answer a little bit on each one. Right there, I think everybody that's on this stream right now that's going to take the test tomorrow, you can answer the first part of each one of those questions, and then go as far as you can. And once you get stuck, then move to the next FRQ, and just don't worry about it. Go, and then if you get the first part of all of them and do everything that you can on your first pass through the FRQs, then go back and try to pick up some more points. And that's about it. So we've gone about an hour and 15 minutes. What comments do you have? Any other questions for me? And I'll stay on here as long as you want. If you want to do some more problems, I'd be happy to work more problems. I'll just kind of leave it up to you guys, because I got nothing else to do but sleep, maybe. All right. I don't know if you guys know Elliot Henry. He's a famous English mathematician from the 18th century, and the lines that we draw when we're doing the fundamental theorem of calculus and evaluating integrals, they're called Elliot Henry lines. I don't know if you guys knew that, but Elliot, and I think this is his great grandson that's here. Any other comments? Antonio Guzman. I don't know who Antonio Guzman is. Yep. Oh. On the derivative sheet, what is that's hyperbolic sine, hyperbolic cosine. No, you're not going to be tested on that. And I don't have a good explanation. You know who can explain that really well is, I think, maybe one of the top two smartest people that I know, and that's Nolan Thaler. Well, Nolan is very smart too. But I'm thinking of my other student. Where is he? That could explain that. Noah, not Nolan. Noah. Nolan's smart too, but I'm talking about Noah Touchton, one of my BC students. So that's what that is. But you definitely don't need to worry about that. Is it possible to work? Yeah. So TR, yeah, we can do. I'll do some rotational volume and washer problems. Yeah, that'd be fine. I'll do that. So I'll work some of that if you guys want to hang around. If not, if you want to drop off. And I wish you the best of luck tomorrow. Just enjoy it, right? Nothing you do on that test tomorrow is going to change your life that drastically, if change it at all. So just enjoy it. Just recognize you are I always tell my students, you're like in the top 0.01% of all human beings having been exposed to calculus and knowing some calculus. So take pride in that. All right, so wash your problem. So let me do that. I'll pull up the ones that I think would, I'll pull up some actual ones. That would be good. Some actual problems. Let's see, and maybe a calculated problem. That would be a good one to do. Here we go. Where are the volumes? There we go. I think it's in this first set of problems that I have. Let's drop it into the live stream. And then see if I can get this to work. Yeah, and then we go to here. See, that works. Most of these problems, as we've worked, I'll try to pick one that I haven't worked in class before. I think some of these I have not worked. That looks kind of familiar, but I think, yeah, this would be a good one to work if you got time to hang around. We're down to about 19 people, but let's look at this because this does both rotational volume and base cross-section volume, and then kind of a one that has come up more than once, which we are dividing R into two regions with equal areas. All right, so let R be the region enclosed by the graph of f of x equals x to the fourth minus 2.3x cubed plus 4, and the horizontal line y equals 4 as shown in the figure. Find the volume of the solid generated when R is rotated around the horizontal line y equals -2. This just seems familiar, although all of these tend to run together when you do a bunch of them. So here's the line y equals -2. And we're going to rotate that around that line. And what you want to do here, students, is we are going to limit our integration between those two x values, which we don't. Boy, I'm certain I worked this one in class. This one looks so darn familiar. Can you come by at 7:15 tomorrow? Says Rishi. Man, Rishi, you're pushing it. It's 10:30. Yeah, I don't. I should be there by 7:30. So, and Nolan, the Riemann sum equations with the sigma notation. Oh man, I don't know about that. Maybe. Let's see. Let's get through this. Anyways, what we would do is if we're going to rotate this, we are going to have to stretch a vector from our line of rotation up to the farthest. I'm drawing a straight line as best I can to the farthest boundary of our region. And that's going to be our big R. And then we're going to go with little r to the closest. And then what we're going to do is say, well, the volume of this is going to be pi times the integral. It looks like these things intercept at 0, and they would. That would make perfect sense, right? Because the solution to this would be these two things would intersect at 0, 4. But I don't know the limit over here. We do not know that. I don't think that we do. So that I'll just call that point A. And then what we're going to do is we're going to take big R squared minus little r squared dx. Okay. And what we're doing, right, is we are taking rectangles right here, and then we are rotating those around, coming out of the screen at us around to create a washer, where this rectangle is the solid part of the washer, but all of this empty space is the hole in the washer. And so that's why this is minus little r squared, because we're taking out that volume that's generated by that void between the lower part of our boundary and the axis of rotation. And what we have to do then is just come up with an expression for both of those quantities. So we're going to integrate from 0 to a, and this distance then of this vector that I drew that I called big R is this function, which is 4, minus this boundary, which is -2. So big R is always 6, and that would be squared. And then minus. And then this one right here, this is going to be minus f of x minus a -2. So this would be x to the fourth minus 2.3 x cubed plus 4 minus a -2, also known as plus 2. And then that would be squared. And then we would wrap this up in one big, beautiful dx blanket like that. Okay, and that would be our integral. Now, if I remember right, believe that this is a calculator problem. Let me confirm that. See if I can find some notes on this. Yeah, this is definitely a calculator problem. And what we have to do, I think, though, we could find out this A, I believe, when we set these equal to each other. Yeah, they would have to intersect at 2.3. Yeah. So if you wanted to find this other boundary of our integral A, if you set the two equations equal to each other, you get x to the fourth minus 2.3 x cubed plus 4 equals 4, right? So those 4's cancel each other out. You could pull out an x cubed and get x minus 2.3 equals 0. So that other number is 2.3. So we're integrating from 2.3. From 0 to 2.3 is where we're integrating. I'm gonna pull up the TI-84 here and then show you what this would look like on the calculator. I'm gonna go ahead and put in to y1 my function here. And so this is going to be x to the fourth power. Oops, let's clear that out. X to the fourth power. And then minus 2.3. Whoops, a daisy. Whoops. Just like class, isn't it? That's one of my most common errors. Okay, x to the fourth minus 2.3, x to the third, and then plus 4. Okay, so I've got that entered in. And I won't bother putting in 4 there. I'll just use 4 as the function. So I'm going to go back to my home screen now. And then this is my integral right here, right? I'm going to get, for this volume, I'm going to get a decimal answer. So I'm going to put this whole thing in just as I have it shown right there. I'm going to put a pi in. I'm going to call up math 9. I'm going to integrate from 0 to 2.3. And inside here, I am going to realize that that's 36. 4 minus negative 2, 6 squared, 36. Minus. And what I have here is just in parentheses, I have to call up my function, y1, and then I'm going to add 2, right? Because I would be subtracting a negative 2, and then I square that. Like that. Shalini says, why can't you do u sub on that one? Oh, wait, is that natural log 2x? I'm not sure what you're referring to there, Shalini. Yeah, I'm not sure what you mean. Tell me what you mean. But anyway, so when I execute this, let's go back. Maybe I'm missing a parentheses here. No, I didn't put my dx in. I knew I forgot something. And so then we get this answer. And that should be the right answer. I'm going to pretend that it's the right answer. No, but it is the right answer. Another tip, right? Always, if you're using your calculator, you had better answer to 3 decimal places or you will not get credit for that point that would represent the answer. You can truncate or you can round. So they took on this one, they took 98.868 or 98.867 as our answer for that volume right there. Okay. All right, cross-sectional area. I mean, this is the kind of problem that you definitely are going to see on the test. I mean, I just can't picture, I can't think of a test where they didn't have one of these, where it was a multi-part problem with cross sections and volumes from rotations with washers and discs. But B says R is the base of a solid. For the solid, each cross section perpendicular to the x-axis, so we're talking about cross sections perpendicular to the x-axis, is an isosceles right triangle. Oh my gosh, this is worst case scenario. Well, not worst case, almost. Isosceles right triangle with a leg in R. Okay, so they're just telling you that it's one of the legs, not the hypotenuse. That means that if you're standing over here and you're looking in that direction, what you would see coming up out of the page at you, right? We're use those two dots as our reference point. What we would see is those two dots on the page, but then I would see an isosceles right triangle with one of the legs laying on the floor. So it would look like that. And that distance right there, since this line up here is 4 and this down here is f of x, this is 4 minus f of x right here, that distance. Which means since this is isosceles, that's 4 minus f of x. And then I could write a formula for the area of that cross section that I'm looking at, right? That's going to be 4 minus f of x squared times 1/2. So I'll put the 1/2 in front here. 1/2 times that. And then what I'm going to do is I'm going to add up all of the volumes of those tiny prisms that are triangular prisms that have a depth to them of dx. And therefore, for part B, my volume would be the integral from 0 to 2.3 of my area function. I'll pull the 1/2 out front. This would be 4 minus f of x squared dx. Now, one note here, class, I could have written that part as f of x. I did not need to put in the actual function itself. I can refer to the function since it's defined in the problem. And then if you were to do this one on your calculator, you would put that into your TI-84 just as it's shown there. And that's going to look like this. Let's bring that down out of that live thing there. Yeah, so I'm going to I'll do 0.5, math 9. I'm integrating from 0 to 2.3. I'm going to have to put inner parentheses here because I'm going to square this whole thing. I'm going to do 4 minus alpha F4 to call up Y1, close the parentheses, and then square that. And then go with dx. And then pray for the best. And that's the right answer. If it's not, I'm going to lie. No, it's the right answer. 3.574 is the right answer there. Let's take a look at part C. This says that there's a vertical line x equals k that divides R into two regions with equal areas, right? But do not solve an equation involving an integral expression whose solution would give you the value of k. Well, let's zoom in on this just a bit. So we're just saying that, gee, somewhere I would be able to place a vertical line that would cross here at k such that these two areas would be the same. And I want to come up with what that would be. Well, if you think about that, that's not the hardest thing in the world, because I would basically be breaking this up into two integrals is all that I would be doing. I would say, well, this area right here, I would integrate from 0 to k, and my area would be, right, my area is going to be rectangles bounded on the top by y equals 4 and on the bottom by f of x. So I would call this 4 minus f of x dx, like that. And I want that area then to be equal to the other integral, whose area would be starting an integral at k and integrating out to 2.3. And that also would be 4 minus f of x dx. That's it. Okay. Oh, my picture has it covered. My goodness. Anyways, that is what part C is. If you haven't looked at the grading criteria of these free responses before, this part A was worth 4 points here. So this was 4 points. It gave you 2 points for coming up with the correct integrand. So presumably they would have given you some partial credit, although they don't really tell you how they would have apportioned those 2 points or when you would have gotten 1 point. But that was worth 2 points. Yeah, the integrand was worth 2 points. I'm sorry, the integrand. It was the inner part of this integral. It was this part. If you had the right integrand, that was 2 points. If you had the right limits up there, that was a point. And then the correct numeric answer was the 4th point. All right. Mr. Rich, your face is in the way of the answer. I know. I finally got it out of there. Yeah, that's terrible. But, what's more important, the answer or seeing my face with the math hat on? I don't know. We'll see. Anyways, what was I saying? Oh, yeah. So, and then part B was worth 3 points, 2 points for the integrand. Here, getting that correct integrand, and then 1 point for the answer, and then 2 points for part C. All right. Hey, Spurthy. Look who's here. If they give an f of x graph and ask when f prime of x is positive and decreasing, what does that mean, says Spurthy. I don't know. I'm not sure. What that would mean is f prime of x is positive, and decreasing means you'd have to find when the second derivative is negative, presumably. Okay. I don't know if that answers your question there. So you would you'd either want to graph like if it was a calculator problem and they gave you f prime of x, then you could actually graph the derivative and then see where it dips, where the second derivative dips below the x-axis, because that would, when the second derivative is negative, that means f prime was decreasing. Okay. Yes, a very nice avatar there, Spurthy. I have to compliment you on that. William's correct too. When the slope is positive, yeah, but the graph of f of x is concave down. Sure. I mean, when f prime of x is decreasing, then that tells me that that's going to be a region where f of x, the original function f of x, would have been concave down, right? So that is true too. And Nolan says when f prime of x is positive, f of x is increasing. Yep, definitely. So you can make inferences about f of x or f double prime of x based on the behavior of f prime of x. For sure. Yeah. William Lee. William Lee, whose class are you in, anyways? I hope he's not in my class because I don't. And then it would mean that I missed him all year long. But he says, do we need to know the derivative rules for exponentials and logarithm? It was something that was emphasized in a lot in class for me. Yeah, definitely. I put a link in here on the rules of derivatives, but rules for exponentials and logarithms. Yeah, I mean that's like a really important part of this class is exponentials and derivatives. Yeah. I don't know if I even have a set of rules available other than the one that I had posted here. Not real handy. Anyways. All right. Other questions here? Just looking through here. Oh, William asked it again. Oh, Mr. Peterson's. Yeah. Just looking here. Yeah, no, I know. My face was in the way. And that ice cream cone is in the way of your face, so I can't see your face totally because that ice cream cone. Oh, wait. Nolan's got a good question here. I missed Nolan's question. Representing a previous comment where no was actually to do can. Oh, okay. I'm way behind here. Okay. Uh-oh. Spurthy has a very specific question. Oh my gosh. Are you serious? Yeah, what I would do is Wolfram Alpha. That's what I would do on that one, Spurthy. So, okay, let's see what Spurthy is talking about here. I don't know. Integral, I assume that you're talking about tangent to the sixth power of x secant squared x dx. I think that's what Spurthy's talking about. Yeah. Huh. That's a good one. Well, let's see. So I'm going to use U substitution. That's what I'm going to do. I'm going to use U substitution here. So what I do, I would let I'm going to let U equal something so that when I take the derivative, I get the other thing. So I'm going to let U equal tangent of x. And, class, don't forget, right? This is tangent. That's what that means. So I always recommend rewriting it like that. And therefore, du is secant squared x. I'll write it like that, dx. So then my integral shall be u to the sixth. U to the sixth du. So then my answer is going to be u to the seventh over 7 plus c. So I'm talking tangent seventh power x with a 1/7 in front plus c. I think that's it. Uh-oh, TRR's got a big, long question. I don't know who TRR is. It's almost my initials. For the FRQs, it's important to not overuse pronouns. And your clearly state fx is increasing because f prime's not the function. Oh yeah, that's like super bonus tip number 3 by TRR, right? You never want to say it is doing something or the function. You want to be very specific on what you're referring to. Yeah, without a doubt. That is something. Oh, that's one check to look at your FRQ answers when you're told to justify your answer and you're saying it is increasing or whatever. So make sure you're talking specifically about the function. Thanks there, TRR. Pretty awesome. Pretty awesome. Amit Gupta. I had you last year. Oh, that's who you are. Oh, awesome. Amit, what's with the TRR? I'm sorry, I just had to ask. Okay. Jacob, should we also know that arc cosine x? Oh yeah, sure. I mean, that's one of the rules of your derivatives that you want to know, that when you take the derivative of the arc cosine, that it's -1 over the square root 1 minus x squared, and arc sine being a +1 over square root 1 minus x squared. I mean, they're not the most common things that you run into, but I think it's safe to say that on every test, maybe at least one multiple choice is going to have something to do with arc trig functions. And then Tyler said, "Is the unit circle important to know?" Yeah, definitely. I mean, that's if you don't know the unit circle, it's going to cost you some points on the non-calculator part. Usually, though, it just seems that my experience on these problems is they're not asking like maybe the most obscure unit circle questions. Sometimes you can get by with just knowing, maybe the 90, 180, 270s, or the middle quadrant angles, the multiples of 45. But definitely, yeah, unit circle is big. All right, so Nolan was asking about going over the Riemann sum notation. Yeah, I'm gonna have to find a few problems on that. Let me see if I can. Let's see. Let me see. We still got 16 people here, so let me see here, Nolan, if I can find something for us to take a look at. I got some stuff in here somewhere. Somewhere. Where would it be? Yeah, I think it's over here. Boom, 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 boom. I'm looking. I am looking here. Man. Well, let me just paste this over here, and maybe this will be something we could use. Just what is the definition of the definite integral in terms of an infinite sum of infinite Riemann sum? I guess is how I would call it. Let's see if I can paste this over here into the live stream. See if this works. Maybe. All right. When we first learned about integrals and the fact that they represent area under the curve, in fact, even before we learned how to take antiderivatives, in our class, we just said, okay, here's an integral. Let me show you what it is in geometry, using geometry to find areas and then knowing that that's equal to the integral. But really what we're doing, this integral comes from the fact that we're taking a sum here of rectangles, where we're evaluating our height of the rectangles at some arbitrary x of k times delta x, some finite width. And we start with k equals 1, so that would be x1, and then we would go to k equals 2, and we'd find the height of the next rectangle. But then what we do is we say, well, wait a minute, how about if we just use an infinite number of rectangles and let n go to infinity? Then what's going to happen? Well, over here, this is what x of k is, right? A is our starting point of our integration, and then we're going to go over delta x every time we increment k. Well, what's delta x? That's going to be the difference in our the difference over our interval that we're integrating divided by the number of intervals. But we end up letting n go to infinity, so delta x approaches 0. So, and then there are usually some problems on multiple choice where you have to match a problem that's written in this form back to the actual integral. And you can usually figure that out, right? If you know these definitions right here of what the x of k represents and what delta x is, right? Because this is a 1 over n, right? This is b minus a and then times 1 over n. So you're looking for there to be a 1 over n as a part of this, and then you can kind of work backwards and find out what the function has to be. I don't know if that's probably not the best explanation. But you know, the thing about it, these are just infrequent questions. So a lot of teachers, myself included, in fact, I don't think we even covered this year in my class, honestly. I think I might have mentioned it once, but I don't think we ever went back and actually hit on it again. What else? We're down to 12 people. The binomial theorem. Oh, man. I think you must be talking about stats, but that's over. Yeah. Sometimes you got to go out of the first quadrant. That's possible. It's good to know. You definitely want to know or at least know how to write down the unit circle, right? Know the pattern so that if you do get stuck, you could figure out what the value is. All right. Well, hey Nolan, thanks for showing up with all these Stanton people. I appreciate you coming to check us out here. Okay. I'm just searching for other good questions here, but I don't think I see a whole lot. I'm scrolling. Yeah, I better go to bed because Rishi's going to show up at my class tomorrow at like 7 a.m. banging on the door with some questions about infinite Riemann sums here. I don't know. Who knows? You're welcome, Noah. But anyways, all right, everybody. Have a good night. Rest up. And I guess I won't see you tomorrow because I'm not supposed to see you. That would be illegal and I would get in trouble and your score might be voided. So, but I do have some spare calculators. If something happens, you could check one of them out if you leave like $100 for collateral. But anyways. Okay, guys, ladies, I will see you at school at some point over the next week. Have a good night, and thank you all for coming. I really thought it was fun and interesting. I'll talk to you all later. Bye. All right, William, good. Glad that you found it helpful.